Okay, let's get started. So today, before we talk about more theories, we will do data analysis in RStudio. Okay, so I'm going to send these 3 lines of code to you in a chat box. Okay. Okay. Now, what we are going to do is we will open our File Explorer, and then, as usual, we'll go to Drive C, and then I think we already have a folder exercise_SWR, and open the folder, and there we have already have some file. Okay, so we copy this one or anyone. Okay, any file, you can copy any files. Okay, R file, and then paste it, and then we are going to rename it as week 3 day 3, right? Okay, anyway. Okay, so we are going to double click and open it. All right. So what we are going to do is, I think you should have some line circuits here. So the first time we write our R script, we should clear our workspace, okay? And then we load our packages, okay? And then we're going to delete everything, okay? Because we are just going to look at the linear regression. And then we will say that, okay, we will import 3 data sets, okay? Which I've already provided the links. So you have to copy the link and then paste the link here, okay? Okay, so it should look like this. Okay, anyway, for the second data set, this data set is the starter format, okay? So this data set is the starter data set format. So we need heaven packages, heaven package. So if you don't have it, then you install it using install.packages, and then you put it in a double quotation mark and then heaven. Okay, so if you do not have the package, this one, I mean, if you haven't done it at the start of our course, then you need to do it. Okay, if you already have it, then it's okay. But okay, so I'm going to put the shift key in front. Okay, so this one means that this line of code does not run. So you can check basically by typing the words, okay, heaven, HAVE, and then this should appear. If this appear, then the package is already installed. Okay, so you don't need to install it again. Okay, otherwise you will have an error. Okay, so these are the, I mean, the shortened URL link. So that's why they don't have the extension like .csv. Okay, but in the I mean, in the original URL link, which is connected to this shortened URL link, it is already there. The extension is already there. Okay, so you don't have to put .csv here. Okay, anyway, so we have 3 data sets, state 1, state 2, and cognitive. Okay, so we're going to look at this. Yes, so heaven is a package. We are using it because we can access the package using this code. Okay, so heaven, and then you put 2 colon. So that means that we are directly accessing the package without loading the data set, okay? So here we load the data set. So it will be in our memory. Okay, so this is the time to run everything. So select everything and then run it. Okay, so this tree data set is online, so it will take some time if you have a slow connection. Otherwise, it should be quick. Okay, so we only have a small number of observations, so it shouldn't take too long. Okay, so we are going to use one by one. Okay, one by one. Okay, so we already discussed the theory in the first few days of this week. But the first thing we need to do is some data exploration, okay? Data exploration. And we are going to start with state one, okay? State one data set, which is the data set that which we have already discussed as an example, okay? So, okay, so we import the data set. The first thing we need to do is explore the data. How do we explore it? The first command is go book. Okay, so you look at the states one, okay, and run it. So we have 6 variable, okay, and 51 observation. So this data set is about the United States or America, and they have 51 states. Okay, so apparently we do not have any missing value. Okay, next. So we already previously we already discussed this example. Okay, what is our response variable? Our response variable is poverty, and we look at high school graduate. Okay, so we will do a summary statistics because these are numerical variable. Okay, so what we can do is okay, these are all data exploration, but we will say it is the descriptive statistics. Okay, to give an idea. Okay, what we can do is we can just put the whole data set to the sum function. Okay, so this function is coming from mstat package. So we can just say that, okay, sum state one. Okay, okay. So if we run this, you can see that every variable that is shown as numeric, where we summarize here. Okay, so starting from metro rest, we have 5 variable, numerical variable. So that is how you do it. Okay, so we can look at here poverty. We have 51 observation. So the mean poverty across 51 observation at United States is 11%. Okay, which is high considering percentages in Europe. And then the median percentage is 10.6. Okay, so the mean and median is around 1% difference. Okay, so we are looking at the distribution. Okay, we are trying to think about the distribution. And then we look at the quantile. Okay, first quantile and third quantile. So the interquartile ranges between 9% to 13.4%. Okay, so around half of the data belongs to this range. So it's rather high. And then the maximum is 18%. Okay, and then the minimum is 5.6%. And then, okay, we can check the normality here. Okay, so this is 0.05. So which means that there is no enough evidence to say that this data is not normal. Okay, so this is for poverty. Then we look at the high school graduate. Okay, the same. So high school graduate percentage is 86% across the United States, and with a 3.7% with 3.7% standard deviation. So this is rather small, right? Standard deviation is rather small. But if you look at the poverty percentage here, this one, so you can see the standard deviation is 3.1 when the mean is 11. Okay, this one is 3.7 when the mean is 86. So it's rather, big difference when you have a small mean. And okay, anyway, we look at the median, which is 86 and 83, but the interquartile range is 83 to 88. Okay, so this is what we got. So the maximum high school graduate percentage is 92%, and the normality, we can say that okay, there is some evidence saying that this data is normal. Okay. Okay. Next, what we are going to do is we are going to look at the correlation. Okay. So basically, we will say that correlation between poverty and high school graduate. Okay. Okay. These are already discussed previously, right? So I won't take time to explain what is what. Okay. So we will use the Cordo test, which is already testing the correlation and show the correlation result as well. Okay, so we can say that okay, how do we use correlation? If we don't know, we can look at by stating question mark and then core test. Okay, and how do we use this? We can use using formula and data. Okay, so we will say that okay, how do we write the formula? With the tilde sign. Okay, so we say that poverty and the tilde sign, and then you say the high school graduate, HS grad, and then we say data is from states 1. Okay, wait, okay, I think this one is like this. Okay, so if you're not sure, you have to check in the example. Okay, so you have to write like this. So the tilde sign at the front. Okay, write the tilde sign first, and then put your poverty, HS, and HS graduate. State the data set. Okay, so we are going to run this again. So anyway, our correlation between poverty and high school graduate is the negative. So we can say that is a little bit fairly strong association. Okay, so negative strong association. So we get correlation minus 0.74. Okay, and then p-value is this one. Okay, so significant. Okay, so this is our correlation, but we want to look at the linear regression. Okay, so before we run a linear regression, we have to first we need to look at the scatter plot. Okay, it's a good idea, always a good idea to look at scatter plot first before you do the linear regression. So scatter plot of poverty and HS grad. So we will use the plot function. Okay, so we will look at the plot function quickly. Okay, anyway, so I didn't see any data option here, so we will have to specify data with the function width. Okay, so with the function width, we will say that the data set is states 1, and then we say plot, and then we can just put poverty and what is the second one? HS grad. Okay, so I'm going to give it a little space so that the plot will appear nicely. Okay, so this is our scatter plot. So I'm going to expand this, So you can see that we have the scatter plot between poverty and HS graduate. Okay, but actually I'm going to make a little bit change because there is XAZ. Okay, because when we talk about linear regression, we always we always think in terms of response variable and explanatory variable. And poverty is our response variable, so we always have want to put it on y axis. Okay, so we just have to change these axes. So I'm going to delete this and put HS graduate first, okay, high school graduate first, and then poverty later, second. And then this will just change the axis. Okay, so now on the x axis we have high school graduate percentage. So anyway, the scatter plot, even the correlation coefficient does not change. Okay, even when you switch x axis and y axis. Okay, anyway, we can see that the negative linear association. Okay, so okay, we can say that we can use the linear regression. So let's go on with the linear regression. So this is called a simple linear regression. Okay, because we have one response variable and one explanatory variable. Simple linear regression. Okay, because we have one explanatory variable. Okay, so if you are not sure, then you need to spell it out. Okay, what is our response variable? Our response variable is poverty, and our explanatory variable is HS grad. So I think this is a good idea to spell out what you are going to do and what is what. Okay. Okay, so there are two ways to do this. Okay, the first one is using Amstead package. Okay, and the second one is using BESA. So let's anyhow we use Amstead now. So let's start with Amstead package. So the function for linear regression is regress. Okay, so you put a regress. And anyway, it is a good idea to check the documentation. So go to the console. Give it a question mark and then type regress. Okay, so this is coming from Amstead package, linear regression model, which produce the regression output with which mirror outputs from Stata. So basically, the outputs are very similar to Stata. Okay. Okay. Anyway, what are the outputs? And the outputs information about the model and about errors, which we haven't talked about it. Yeah, because we stopped yesterday just before the error. So we haven't talked about this yet, but we extensively talked about regression output. So anyway, let's go on with the simple linear regression. Okay. So how to use this? So like I said, every functions in Amstead, almost every function in Amstead start with data argument. So you can just say that, okay, the data set is dates 1. Okay. And then y is our response variable. Okay, so that's why we put the poverty on y axis. Okay, so you have to start with y. Okay, and then you remember there is a dot dot dot. Okay, which means that you can put many x. Okay, but right now we only have one explanatory variable. Okay, so we will say that okay, our y is poverty. And then our x is, okay, but we cannot say here, we cannot say x here, okay? We just have to give the name. So anyway, if you remember the orders, then you don't have to specify y, that the word y is equal to. You can just put our data set and then the response variable, and then we put the explanatory variable, which is HS, correct. Okay, that's it, okay? Right now, that's it. And then I'm going to drag it down so that we can see the output clearly, okay? Okay, anyway, this one message is coming from the plot because we have so I'm going to clear this. So okay, I'm going to clear the console. How do we clear the console? By pressing Control L, okay, so that everything is clear. So I'm going to run this again, okay. Okay, so this is the linear regression model outputs. Okay, so there are a lot of information here, but what I want you to focus, okay, what I want you to focus is this table and the first table and the third table, okay. Every information is important, okay, for a linear regression, but don't be intimidated by this, okay. Just take it easy, relax, and I will explain which importance. Okay, so right now let's look at the this is the information for the linear regression model. Okay, so the first thing we need to look at is the number of observations that we use in the regression. Okay, sometimes when you run the regression model, if there are missing value, then the regression model will drop the missing value, missing observation, which means that you will have less observation. Okay, so you always need to check this observation number. Okay, so our original data set have 51 observation, and our linear regression model also use 51. So it's good. Okay, and the second status is this one, R square, because yesterday we talked about R square. Okay. Okay, so let's look at this R square, which is 0.558. Okay, this is wrong. So we can say that, okay, the variability in percentage, around 56% of the variability in poverty can be explained by this model. Okay, so which means that there is associate. I mean, the model is doing quite well, 60%, around 56%. Okay, so as of now, okay, there are two information. This two information is important for you. The rest you just ignore at this moment, and we will come back later. Okay, when we go on with the theory. Okay, so we now know that we use 51 observation in our linear regression analysis, and then our model, this model, can explain 56%. Okay, which is good. And then we move on to the last table, which is a regression output, which you already familiar with, right? Okay, so right now we have the poverty, which is our response variable, okay? And we got the intercept, and we got our explanatory variable, okay? And on the next column, we got coefficient, which is the linear coefficient, okay? Which is our beta 0, which is intercept, and beta 1, which is for high school graduate percentage. Okay, and then we got the standard error, okay, which are not that important in this case because we already have our 95% CI and P value, okay? Okay, so there is a question, what is the adjusted R square here, okay? So the adjusted R square is the R square adjusted for multiple explanatory variable, okay, which we haven't discussed yet. Okay, so right now, that's why I said we only look at the simple linear regression with one explanatory variable. So just ignore these statistics at this point. Okay, these are used when you compare multiple models. Okay, so when you have 5 other explanatory variable, and then you will build several models, okay, including and excluding variables, and look for the best model that describe your data. In that case, we are going to use this statistics. Okay, right now just ignore this because we haven't discussed yet. What we have discussed is our observation and our R square. Okay, and we didn't even discuss this yesterday. We just stopped before we start this theory. Okay, this discussion. Okay, so that's why I said you only need observation and look at observation and R square at this point. Okay. Okay. Anyway, so like our correlation coefficient, and now we can quantify that. Okay, if there is a 1% increase in high school graduate, and then we can see that, okay, 0.6, okay, 62%, oh sorry, 0.62% decrease in poverty. Okay, and it is significant. And how to interpret the 95% CI? So we can say that if there is 1% increase in high school graduate percentage, then we can say that our true poverty percentage lies between zero 0.776 and 0.466. Okay, so these are the 95% CI and the p-value. Okay, any question at this point? Okay, so next, so we have finished one. Well, we have finished. Anyway, we have finished this. Okay, so the question is, we can see that the intercept is significant, right? In this case, our intercept is meaningless. Okay, when we look at the linear, when we look at the linear regression line, the intercept is used to make the start of the linear line. Okay, because think about the definition of the intercept. So intercept is when the explanatory variable is 0. Okay, so when there is no explanatory variable or x is equal to 0, that is the poverty percentage is equal to the intercept. So we have to say that if to interpret this intercept, we have to say that high school graduate should be 0%. Okay, which we discussed yesterday. Our data set range from when you look at the summary statistics again. Okay, so our data set range from high school graduate, the minimum is 77%. Okay, so 0% is way beyond our data range, so we just call the extrapolation. Okay, so that's why it is meaningless to interpret intercept and even use the p-value. Okay, in this case, so that's why we only focus on the slope. Most of the case we only focus on the slope. Okay, so if there is a meaning when x is equal to 0, then you can interpret it. Okay, but rarely that is the case. So we only look at the slope value. Okay, so let's try with other example. Okay, so let's run this codebook again. So we have other variables. Okay, we have other variables. So we can, but anyway, we have finished calculating the slope and the regression. Okay, but we need to look at the condition and check the assumption. Okay, whether we can use it or not. Okay, so how do we do this? We can do this by specifying the plot argument. Okay, and we look at the plot. You don't have to plot for each assumption by yourself. Okay, so just give it a comma, and then plot is equal to true, which will produce 4 plots. Okay, so I'm going to run this. So wait, I have to run this again. Okay, it's a little bit cranky, so we are going to zoom it. Okay. Okay, anyway, this is how it appears. Okay. You just focus on the plot on the left side. Okay, these are just we haven't discussed this. We didn't discuss this. Okay, so anyway, when we focus on the 2 plot, it is enough. Okay. Okay, so look at this. Based on our scatter plot, we can and look at this residual plot. We didn't see any pattern here. Okay, and we didn't see fan shade, or we didn't see any ups and downs. These are randomly distributed around the 0. So we can say that, okay, so this is the residual plot. So we can say that, okay, linearity assumption is met. And then look at here, these the data is, there are some points that are not on the dotted line. Okay, so the linearity assumption is there is some problem. Okay, it is the standard residual, and it is the QQ plot. So there are some problem. Anyway, and okay, so this is the same residual plot, but what they do is they standardize the residual. Okay, so that this one is a little bit scattered, so this one is standardized and square root, so that starting from 0. And the same, you can look at the pattern. You always have to look at the pattern on this graph. So you can say that, okay, there are no obvious pattern here, so we can say that linearity assumption met, and we can say that there is a constant variant assumption met. Okay, but normality assumption is not, but it's not quite severe. We have 51 observation, and then it is slightly skewed. Okay, but we will look at the we will look at this later. Okay, but right now it is a little bit skewed, but we have 51 observations, so we can say that, okay, we can just skip it. And then there are like the measurements to what this graph is looking at is the leverage point. Okay, basically to identify the inferential point, but obviously there isn't any inferential point here. Okay, so any obvious outlier here? No, the data are scattered around here, so no obvious pattern. Probably this one. Okay, 27 and 40. But as you remember yesterday, if we remove this 27 and 40, and then the slope does not change, then we can say that, okay, these points are not inferential point. Okay, so we can just put it. Okay, so for the sake of demonstration, let us look at how to do that. Okay, so based on that plot, this plot, we now know that 27 and 40 something. We now know that 27 and 40 is a little bit tricky. But I mean, it is for demonstration, right? These are not inferential points. Okay, so say we have 27, the 24 observation is assume. We we need to check. We check for differential point. Okay, so what do? We remove this one. Okay, this is the 24 position of the data set. Okay, so one way to do this is we create a data set. Okay, we specify the data set and then we subset it. Okay, this is a little bit data management skill. Anyway, we can look at this. What is the 24 position? Is the Minnesota. Okay, 24 position is the Minnesota. So we are going to remove the observation with the Minnesota. Okay, so this is the data management now, but we will combine it with the linear regression anyway. So we will say that okay, this data, and then we will use the piping function. Okay, so we put the data set and then push it downward, and then we say that we will filter. Okay, how do we filter? Wait, I'm going to declare this again. Okay, state. Okay, the variable is state. State when state is not equal to Minnesota. Okay, so we filter state, which is a variable. Okay, which is not a data set, which is a variable. State not equal to. Okay, so we will say it's not equal to. So it's equal to is symbolized by two equal, right? So it's not equal to is symbolized by exclamation mark and equal. And then we will say Minnesota, and then we put it the same. Okay, yeah, we put it the regression, but when we use this one, we just ignore, we don't have to mention the data set. Okay, I think that time limit is almost up, so when it's closed, then you just reconnect the meeting. Okay, so I'm going to run this. Wait, okay, this should be state one. Okay, so when we remove the Minnesota, it barely changed, right? So that's why I said it's not inferential point. It is for the sake of demonstration. So this is how you remove the observation from the from the data set. Okay, and then you ran it. Okay. So I think we checked our assumption. I mean, three assumption. Okay, and I think the last one is okay. So we have our scatter plot here. Okay, so you have to remember when you run the plot is true, you need to turn it off. Okay, turn the graphical parameter off by turn the layout for graph. Okay, how to turn it? The device off. Otherwise, it is annoying, right? So there are 4 layout because we already ran this one, so we remove it. And okay, just trying to run this one. Okay, I think someone has a question. Oh, it doesn't matter. I mean, you have to look at the plot, and then I remember it's 24, but okay, that is 27. So it doesn't matter. I just want to demonstrate it, how to remove the observation from the data set and then run the regression. Okay. So okay, 27 is Montana, and probably that's why we didn't see any. Okay, let's do that again. But I mean, it doesn't change much. Okay, so from minus 0.60 something to minus 0.65. So only two decimal point, a 2 decimal point change. So it isn't that significant. Okay, so any questions? If not, we will continue with the second method to run linear regression. But I mean, this method is a little bit, use base R, so you have to subset and do something with a model. Okay, so if you don't want to follow this one, you can just sit back and relax and watch it. Okay. Okay, so the regress function is from Amstack, so that's why when you do this, every output is already processed. Okay, for you to use the information, and even you can look at the plots. It's already there. Okay, to use second method to use base R. Okay, so to run this, we are going to look at the linear model, okay, which is denoted by LM, okay, which is the base R function. There is the staticist, okay. So this LM is used to fill linear model, and then we can use formula and data. Okay, so that's what we are going to do. Okay, so let's write this LM, because there is a data set, so we don't need to specify data set with function. Okay, so we say what is our response variable? Poverty. Okay, and then we need to put the formula here. Okay, remember in regress function we do not have to put any formula. You just to specify the data set first. If you're using piping function, no need to mention the data set, and then you put the response variable and then the explanatory variable. Here the sequence is the same, but you have to put as a formula. So how do we write formula? With the tilde sign, okay? And then we give HS graduate, okay? And then data is equal to states 1, okay? You need to correctly spell it. Okay, so that's it. That is the first step for the linear regression in base R. Okay, so we are going to run this. Okay, I think the plot function is a little bit annoying, so we will turn it off with the device of function. Okay, so let's do it. So when you run it, it just gives you this, okay? This call and then the coefficient intercept, just the coefficient. Okay, so what we are going to do, what we should do is we name this output, okay? We name this this regression model. Okay, so let's give it as LM dot. We say that it is LM dot HS graduate. Okay, we will say is explanatory. We will combine it with explanatory variable. So we name it as the LM dot HS underscore graduate. Right. Okay, so when we run this, you will notice something will appear here. Okay, so this is called assignment. Okay, we are assigning the result of this linear model fit. Wait, run. Okay, so here we got lm.hs underscore grad, okay, which is not a data set, which is a list, okay, which is a list. And okay, this is the first step when you use base R. The second step is you have to use the summary function to summarize to summarize this lm.hs underscore grad. Okay, it is the summary, not a sum. Okay, not sum. So write this hs underscore grad. So run this again. Okay, so right now we got some information here. Okay, so we got the how we ran this. How we ran this. I think it is same as the is the output here, the formula here. Okay, the same formula, because in Amstrad the regress function use lm function behind a scene, but it just process for you so that you can use it easily. Okay, so here it's a little bit so this is the function that we ran this regression. And then it is information about residual. So you can look at the median is around 0.2 minus 0.21. So these are the residual summary. And then we got the coefficient information, okay, the same as above. And then you can read it, okay. This one is the same. And then there is a p-value. And then we got some residual standard error, RSE, on 49 degree of freedom, which is coming from the variability partitioning, which we haven't discussed yet. And it is also multiple R square, and then R square, just the R square, which the same. Okay, so it's a little bit clunky, and otherwise you can just ignore this at this moment. Let's focus here. So anyway, we get our coefficient, but the problem, and p-value, the problem is it does not give you the 95% CI. Okay, so in order to get that, you need to, so by running this, the second step, you will get coefficient and p-value. In order to get so this one we got intercept slope, also p-value. Okay, you get these three numbers. To get 95% CI, what you need to do is you need to run confit. Okay, the function confit. Okay, confidence interval. That is the short for confidence interval, confit. And then you put it the linear model. Okay, so you get the 95% CI. Okay, so this is how you do the linear regression model in base R. Okay, in order, so but there is no plot. Okay, so to get the diagnostic plot, you need to plot the linear regression. Okay. Okay, so this is, so when you do this, you will get this one, hit return to see the next plot. So you can see the 4 plot one by one. Okay, this is the same plot that we have seen here. Okay, this plot is going to true. This is the same option, but here you only get one plot one by one. Okay. Okay. Anyway, you can look at this. So this is how you do the linear regression in R. Okay, one more thing, but this is one of the, I mean, this is one of the disadvantage. One of the disadvantages if you use regress is you cannot draw a histogram of the residual. But still you can do it, but you have to do the same step to draw the residual. So here, draw histogram for residual. This is to check the assumption, okay, for whether the residual are not nearly, I mean, normally distributed. Okay, so we say histogram, and then we have to specify the model, okay, lm.hs graph, and then we have to subset using $sign, and then we have to put it residual. Okay, I think it's fairly normal. Okay, it's fairly normal. Okay, so this is the way to conduct linear regression model in data, okay, using LM function. But here you just for answer you just have to remember this regress formula, okay. One of the nice thing about this is you can also assign this output, okay. But we will talk about it later this week, because at some point we need to export export this number to Excel, okay, Microsoft Excel, to create tables for the publication or something. So there is a function to do this, okay, in Amstrad. Okay, anyway, so any questions at this point? Okay, so why don't we try the okay, so why don't we try with the other variable, okay, in stage 1. Let's look at the other variable. Okay, so we have our response variable is poverty. Okay, we want to know what other factors associated with poverty. So the first thing that comes into our mind is education. Okay, and then we say, okay, if the what is the, is there any relationship between the percentage of white people living in that state and the percentage of poverty? Okay, so we will look at that. So we look at the poverty versus white. Okay, this is all one by one. Okay, simple linear regression. Okay, so before we do that, we just need to look at the scatter plot. Okay, so we say that state 1, then plot. How do we plot poverty and white, I guess? So we draw, okay, I think put it in the middle. Okay, anyway, this one is X, so we need to reverse it. We want to put poverty on the y-axis, okay? Okay, wait. So as you can see that, right, these data are obviously influential points. Okay. So there are two states, okay, which is below which are quite away from the rest of the data point. Anyway, you just have to be careful about that, okay? And then we look at the correlation, okay? Correlation with the, okay, how do we write this? With the tilde sign first, and then we say poverty plus y, and then data is coming from state 1. And you don't have to remember all these functions because you have the reference, okay? So you just copy and paste and change the corresponding variable. Okay, so you can see that this correlation is not that significant. I mean that strong now, right? Around minus 0.3. Still, because of these outliers, we have some pretty, how do we say, negative association. Okay. Okay, so what if we remove it? Okay, we remove that outlier less than 50%, okay, in white proportional percentage of white people living in the state. Okay, okay, we will remove outliers of white less than 50. Okay, so we already talked about this state 1, and we put it into the piping function, and we will use the filter, of course, right? Filter if white, okay, we want to remove it if it is less than 50. Okay. Anyway, it doesn't matter because there is no point at 50. So we will say that, okay, we'll only take observation if the white is greater than 50. Okay. Sense? And then we will run the correlation again. Okay. Order test again. So we can just copy this. We can just copy this, and then so when you use the piping function, the data set is always have to change to white. Okay. We just this is not mstat function. If it is mstat function, you don't need to specify the data set. Okay. Okay. Anyway, okay, run this. Okay. So even when we remove it, there is some correlation. I mean, the correlation is a little bit stronger, right? 2% more. Okay, so correlation is now 32%. Okay, anyway, so we can say that, okay, even if we remove the outlier, the correlation is still there. So we can say that this cannot be high leverage point or high influential point because it does not change the correlation that much. Okay? So now we will run the simple linear regression. Okay, why don't we just say SLR, okay, simple linear regression. Okay, so we will run regression 2 times. Okay, so 1 time we will just put all data. Okay, so we will say regress and put all data. And then what is the response variable? Y is poverty. And what is the explanatory variable? Y. Okay, in this case. And then we will look at the slope. Okay, and the slope is, you see, correlation is around 32, so it's weak correlation, but some linear association is there. But you see, this is not contributing that much. Okay, so if there is 1% increase in Y, the poverty percentage decrease only 0.06%. Okay, so which is fairly close to 0. So it's not that strong between the 2 correlation. Okay, this is called the effect size. Anyway, but anyway, p-value is saying that significant. So we can say that, okay, this is not exactly 0. Okay, this coefficient is exactly not 0. So there should be some association, even it is not strong. And then why don't we remove the outlier? Okay, the same. So we just copy this. Okay, we just copy this, and then we use this one. Okay, because we use the piping, so we remove the data set. Okay, we do not have to mention it. So we run it again. Okay, so when we remove it, remove the outlier. So you see the coefficient is become stronger, right? So you definitely need to check why this is the case, okay? Why this is the case. But p-value does not change. Anyway, that's not important. But the coefficient is changed, okay? So these are definitely the outliers. I mean, influential points. So why don't we check the plot for each regression? So we say plot is equal to true. Okay. So we run this fast. Okay. So we are going to look at the plots to diagnose the linear regression. Okay. Okay. So you can see that there is a pattern there, right? I mean, the data is scattered here and quite, you know, very few points around here. So there is a pattern. I mean, and the constant is not that, I mean, obviously it is the outlier, okay? And then when you look at this one, so you can see that these points are outside the red dotted line, okay, which is obviously the inferential point, okay, which is obviously the inferential point. But you can see that the residuals are normally distributed, okay. And based on this, okay, we can say that okay, the points are, I mean, the points are scattered around when the value is low, okay, when the filter value is low, and quite few data points, residual points when the filter value increases. So we can say that okay, linear assumption is not that linear assumption is not met, and then the constant assumption also we can say okay, not met. But anyway, when we look at the graph, we say that okay, this could be the case where we have high inferential point, okay, inferential point. So we look at another regression model with the inferential point removed, okay, which is this one. Okay, so you can now see that this data point is quite scattered quite nicely, okay, randomly around zero. So we can say okay, linearity assumption and constant variability assumption is now met, but the normality is a little bit, you know, but we can say that okay, we got 51 observation, we can say that it's okay. Okay, anyway, when you look at this, this is called a Cook distance, okay? There is a formula to calculate this Cook distance. Whether the data point is quite far from the rest of the data so that we can call the inferential point or not. Okay, this is called the Cook distance. And then we look at the standardized residual versus the leverage point. But anyway, this is not important now, okay? To look at the inferential point, you can plot the scatter plot and look at if there are any points that are horizontally away from the rest of the data. These are just statistical methods that, you know, determine the cutoff point to say that, okay, to declare that point is inferential. Okay, anyway, this is how you remove inferential point and run a linear regression if you have such inferential points, okay? So as of now, we are just doing the simple linear regression, okay? So I think there are a few more variables that you can test, okay? But anyway, don't worry about too much about that, okay? And you can do it in your free time and exercise the skill to interpret, I mean, to look at the diagnostic plots. But anyway, we will talk about it. So there are a few more data sets like this one, okay? What is the percentage of resident living in metro area, okay? And then what is the, okay, the last one is what is the percentage of female in a household, okay? So you can look at these two and run a simple linear regression and try to interpret the slope and then p-value and 95% CI, and as well as look at the diagnostic plots, okay? But if you are keen and interested in doing more analysis, then you can also look at the stakes 2, okay, which is completely different data set, okay? Let's just look at the stakes 2 data set, okay? So when you look at the stakes 2, it's already with the label, okay? That is the case when you, I mean, if the data is provided with label and supplied in Stata format, okay, which can store the label, and then when you load the data set, it is already, the label is already there. But if you remember, when you read the data set, the data set state 1 is read with a CSV, okay? So always remember, if it is a CSV, there is no label, okay? Always there is no label, because there is no, the CSV format cannot hold the labels, okay? So that is the case. So if it is a starter format, or I think SPSS format, then you this label will be there. Okay, because it is nice, because you can look at the label and know more information. Okay, so region is geographical region. Okay, so you now know that, okay, this is the, if it is the geographical region, then it is obviously a categorical variable. Okay, next we have the C set. It is a mean composite set SAT score. Okay, I think for school-wide, I think. But anyway, we have 51 observations. So I think this is the statewide database. So it just basically means it's aggregate data. Okay. Percentage. This is the percentage of high school graduate. Okay. Previous data set look at the poverty and states. Okay. This one is the high school graduate, and also the mean composite SAT score. Okay, so which is our response variable. Okay, in this data set. So we want to know, okay, which factors associated with the higher composite SAT score. Okay, is it related to the percentage of high school graduates taking SAT? Or is it related to the expenses that the students pay during their primary and secondary school? Or is it related to the median household income? You know, more household income, they can spend more revenue, I mean, money for their children, right? And high, I mean, the percentage of the parents, okay, that does with the high school diploma. So if the parents are more educated, the college is also higher educated, is it associated with the children getting more increased score in SAT? Something like that, okay? So you can try this data set. This data set is coming from US 1990 to 1991, okay? I think the next data set is about the cognitive score. Anyway, we want to look at the children cognitive score and looking at the mom characteristics, okay? So this kid score is our response variable, and then the rest is our explanatory variable, okay? I think I'm going to take a few more minutes and trying to talk about what if our explanatory variable is categorical, okay? Because we haven't covered this yet. Do you think we have such variable in state 1? Let's take a look at this, okay? I don't think we have here, okay? The states are like, you know, the name of each state. So it's not, I mean, we cannot use it yet. Okay, so what we are going to use, we're going to use state 2, okay? State 2 data set. So like I said, we have the SAT, okay? SAT, and then we have regions, okay? I think this one also quite similar to the example we discussed when we talk about the categorical variable. Anyway, let's take a look at this region. Okay, so region is a categorical variable supposedly. So we will tabulate it. Okay, so we will say that tabulate state 2, then we say region. Okay. Yes, obviously this is the region. Okay, so we got 4 category, 1, 2, 3, 4, and 1 missing observation. Okay. Okay, so next we will just summarize our CSAT. Okay, CSAT, however you call it. Okay, so we got 51 observation, and then we got 944 means, and median is 996, and then our median and maximum up to 1093, and this is not exactly normal. Okay, it's fairly significant. Anyway, we will look at the histogram. Okay, we will look at the histogram of the CSAT. Okay, I'm going to drag it a little bit. Okay, so first we need to close this one. Okay, so we'll say that depth of and then we will look at the histogram. Exactly not normal, right? This is not exactly normal, but we have around 434 observations, so it's fairly, I mean, it's fairly large number, we can say. So I think we can go with the regression. So we will run a simple linear regression with the region. Okay. Okay. So why don't we do this? Regress, and then we mention our data set, which is state 2, and then what is our response variable? CSAT, and then what is our explanatory variable? Which is region. Okay. So we'll just do this and look at here. This is not wrong, but it is not the answer we want. Okay, because we want to have category. We have 4 levels of category, and we want 3 slope here. Okay, which is what we expected, but I'll treat this as a number. Okay, as a numerical variable and spit out the coefficient. Okay, so basically it's quite difficult to interpret this. Okay, when it is treated as a numerical variable, so we will have to change it. Okay, region. So I think this is the first time we talk about the data type in R, which is quite different from the data types in statistics. Okay, so let's go to the code book and see what kind of data we have for region. Okay, which is a double. Okay, don't worry about that. That data is a numerical variable. Okay, so this is a numerical variable. So that's why when we put into R treat as a numerical variable. So we have to say that, okay, region, we have to say to R that region is a factor. Okay. Wait. We can just say it's a character. Okay. Factor concept is a little bit difficult. So we can just say it is a factor. So now we're going to delete this because we are going to use piping function. Okay. So we say, okay, state 2, and we put it in the piping, and then we replace, and do you remember replace region with a character version of the region. Okay, previously we changed WBC, if you remember, WBC to numerical version of WBC. Okay, right now we will replace region to character version, which is a text. Okay, so we will make it as a text or character, so that R treat it as a character, so that we will get the level. Okay, if R treat as a numerical variable, then it will give us as 1 coefficient, which we don't want. Okay. Okay, so how do we change to character version? As dot character, the same as we use when we change to numerical version or WBC, right, we did it with the Astor numeric. Okay, this one is Astor character. So you can just type Astor character, Astor color, and then it will appear. Okay, choose that and then put it region. And then next line, and then we say, okay, regress. So when we use the piping function, then we do not need to mention that data set. So we can directly go to the response variable, which is the C set, and then region. Okay, I think it works. Okay, so now you appreciate this, right? So when we change it to the character, are treated as a category, and then I'll change one as the what? Or I'll treat one as the reference and produce the slope for each level. Okay. Okay. So I think the same, we have observation 51, right? So that's why I told you we need to check this observation number, because we have one missing value in region. Okay, so that's why we did not see the full observation. It's used here. And our R squared is 38. So only 38%, around 38% of the region, variability in region can be explained by the model. Okay, so still good. Okay, this is still good if we don't have anything, then it is good. Okay, if we have something, we have to look at it. Okay, anyway, I hope you can interpret this one. So we have two significant, okay, compared to one. So region 2 and region 4. So this is how you do it. Okay, anyway, time is up, so we will stop here, and tomorrow we will talk about more into the multiple linear regression, okay, with several explanatory variable. Okay, if you have any question, just message me or post it on Facebook group. Okay, so we'll see you tomorrow. Good night, everyone.